everyone. Welcome to our fourth lecture on electrostatics. So in this lecture, we are going to go through Poisson's equation and Laplace equation. So initially, we will discuss how we can formulate this Poisson's equation and Laplace equation, and also we will work through some questions. Okay, now let's see how this Poisson's equation and Laplace equation is formulated and what are these equations. Now, we know electric field is equal to minus del V, or electric field is equal to gradient of the scalar potential, this electric potential V. And also we know from Gauss law, divergence of electric field or del dot E is equal to rho over epsilon naught. So here del dot E is equal to rho over epsilon naught, and we can use this E value here from this electric potential, the relationship between the electric potential and the electric field, to this equation. Then we have del dot minus del V is equal to rho over epsilon naught. Then here minus del squared V is equal to rho over epsilon naught. Then del squared V is equal to minus rho over epsilon naught. So this is the Poisson's equation. And so if we look into the variables we have in this Poisson's equation, we have electric potential and the charge density over the permittivity of the space. So if there is any region, in a region where there are no charges, then rho will be 0. So the charge density will be 0. In those cases, we have del squared V is equal to, so now rho is 0, therefore this is equal to 0. So this equation, we call that Laplace equation. Now, what is the significance of this Poisson's equation and Laplace equation? So when we solve this Laplace equation or Poisson's equation in a geometry in a region, then we can calculate the scalar potential or the electric potential V. Once we know the electric potential, then we can calculate the electric field E, and also we can calculate the electric displacement field D. So that is the importance of this Poisson's equation and Laplace equation. When we solve this equation in a geometry, we can calculate the electric potential. Then using the electric potential, we can calculate the electric field and electric displacement field. So this del V and del squared V different coordinate system, we need to calculate appropriately in a Cartesian coordinate system like this, cylindrical coordinate system and spherical coordinate system. So when we go through few questions, you will understand this more. Then we have the uniqueness theorem. So if any solution to Laplace equation or Poisson's equation, which is also satisfies the boundary condition, then it must be the only solution that exists. So it is a unique solution, which means when we solve this Laplace equation or Poisson's equation in geometry, if that also satisfies the boundary conditions, you will know what are boundary conditions. And if the solution also satisfies the boundary condition, then it must be the only solution that exists. So it is the uniqueness theorem. So in general, we as a practice, we can do this to solve Laplace equation initially by considering the geometry. Then we can, if there is only a one variable, then we can easily do the direct integration and solve the Laplace equation. And then we can apply boundary condition. Then also, if the electric field or electric displacement field values are given, or if those are unknown, then we can calculate those. Now let's try to solve this question. Two parallel conducting planes in free space are at Z is equal to 0 and at Z is equal to 0.02 meters, and 0 voltage reference is at Z is equal to 0.01 meters. Electric displacement field is given. So that is the electric displacement field between the conductors, and you need to determine the conductor voltages. Try this. So you can use del square V is equal to 0. Now, if you look into this geometry, what kind of a coordinate system we can use? What do you think? Can we use a Cartesian coordinate system, cylindrical coordinate system, or a spherical coordinate system? So we just have the two conducting planes, one plane here and another plane here. So what do you think? What kind of a coordinate system we can use to solve this question? Anyone? You can either speak or type in the chat. කවුරු කියන්න බලන්න. කවුරු තමන්ගේ idea කියන්න බලන්න මොකද හිතන්නේ? Cartesian coordinate system or a cylindrical coordinate system or a spherical coordinate system we can use in this situation. Yeah, so in this situation, we can use the Cartesian coordinate system because now in a Cartesian coordinate system, what we have is x, y, and z components. So we have a change in the z direction. So we can use a Cartesian coordinate system. Also, if you want, we can also use a cylindrical coordinate system. So in a cylindrical coordinate system also, we have a dependence of this z component. In a Cartesian coordinate system also, we have this dependence of z component. But in a spherical coordinate system, we don't have a direct relation to the z component in a spherical coordinate system. So I'm going to use Cartesian coordinate system. Now in Cartesian coordinate system, del square V is equal to dou square V over dou x squared plus dou square V over dou y squared plus dou square V over dou z squared. So it's going to be equal to 0. Now in this question, the potential, it's only going to be varying the z direction. Do we have any mention about the x component and the y component? So we only have the conducting planes in the z direction, and also the potential, this reference potential is also mentioned in the z direction. So we can say there is no potential difference along the xy plane. Along the xy plane, the potential is going to be the same. Therefore, if there is no change in the x direction and the y direction, we can eliminate these two terms. Then the only remaining term will be dou squared v over dou z squared is equal to 0. So here now it's reduced to a one variable. Therefore, this partial differentiation we can move into a differentiation d squared v over d z squared is equal to 0. Now, how we can calculate the value of v? What we can do to calculate the value of v? What we can do? Anyone? So we can integrate this equation to calculate the value of v. So first I will integrate both sides. By z. So we're going to get here dv over dz. It's going to be a constant. So when we differentiate a constant, it's going to be a 0. Therefore, when we integrate 0, we are going to get a constant. Then again, to calculate the value of V, we can integrate both sides. Then in this side, we are going to get V. It's going to be AZ plus B. Okay. So that is the equation we are going to get for the potential, and potential is a variable of Z. And here, value of electric displacement field is given. So we can use that information, and also zero voltage reference is at Z is equal to 0.01 meters. So I'm going to use these two boundary conditions. First one is zero voltage reference is at Z is equal to 0.01, and electric displacement field is equal to this value. Now potential at 0.01 meters is equal to A. Z is now 0.01 meters plus B. So here this potential zero voltage reference, so 0 A times 0.01 plus B. So this is the one equation we obtained using the boundary conditions. Then in order to calculate the electric displacement field, first we can calculate the electric field. So electric field is equal to minus del V, or the gradient of this electric potential. So since we use a Cartesian coordinate system, we can write AZ plus B. So that is the potential in the direction of Z, or direction of K. So when we differentiate this one, we are going to get A, the direction of K, minus. Then electric displacement field D is equal to epsilon naught times E. Then D is equal to epsilon naught times minus A K. Now here we know the value for electric displacement field. It is 253 nanocoulomb per meter squared in the direction of K, and we know the value of epsilon naught. Only unknown is A. So using this equation, we can calculate the value of A. So calculate this value and let me know the answer here. Now epsilon naught is the permittivity of free space, and epsilon naught value is given here. And if you do this calculation correctly, the value you should be getting is minus 2.86 into 10 to the power 4 volts per meter. Then once we know the value of A, we can use that here to this equation. 0 is equal to A times 0.01 plus B, and then we can calculate value of B. Zero is equal to minus 2.86 into 10 to the power 4 volts per meter, and here 0.01 meters plus B. So B is going to be 2.86 into 10 to the power 2 volts. So it is 286 volts. Now we know both variables A and B, what are the values. Then we can write potential variation along the z-axis. It is equal to minus 2.86 into 10 to the power 4 volts per meter Z plus 286 volts. So this is the potential variation along the z-axis in this given situation. Now, then we need to determine the conductor voltages. So both of these conductors, one conductor is at Z is equal to 0 and the other conductor is at Z is equal to 0.02 meters. So we can apply those two values and calculate the potential voltage at each conductor. So voltage at the conductor at Z is equal to 0. So this term is going to be cancelled out. It's going to be 286 volts. Then conductor voltage for the conductor at 0.02 meters, it is minus 2.86 into 10 to the power 4 volts per meter, 0.02 meters plus 286 volts. So calculate this value and let me know the answer here. So that value should be minus 286 volts. Check whether you are getting that value. Now, when we solved this question, we followed this general procedure. First, we solved the Laplace equation by direct integration. Then we applied the boundary conditions to determine the unique value of potential. And then also we use this electric potential and electric field relation, then the electric displacement field and electric field relation to calculate the given parameters, required parameters. So any questions up to this point? solve So first we did a little sketch and then we selected what is the proper coordinate system that we need to use. And then we identified that is in this situation, it is only dependent on the z-axis. So we reduced the Laplace equation only into a one dimension. And then by direct integration, we solved, we obtained an equation for the electric potential. Then we applied the boundary conditions. We obtained this relation, and then another boundary condition, it is given the electric displacement value. So we obtained the value for this constant A, and then we use this value for A to determine the value for B. And then finally, when we have this electric potential equation, we used Z is equal to 0. There is the first conducting plane to calculate the conductor voltage. Then for the second conductor, Z is 0.02. Then this is the voltage for the second conducting plane. So any questions up to this point? තේරුණාද question එක? ඔයගලන්ට අපහැදිලි දැන් හරි speed එක වැඩිද කොහොමද? Any questions or anything? So if you don't have any questions, let's move on to another example. Find the potential function and the electric field for the region between two concentric right circular cylinders, where B is 0 at R is 1 millimeter and B is 150 volts at R is equal to 20 millimeters. Now, we have two cylinders. We have two concentric cylinders. So the radius of this cylinder, it is 1 millimeter, and we have another cylinder. Radius here, this 20 millimeters. And then the potential along this inside cylinder, it is 0. And then potential along this outside cylinder, it is 150 volts. So we need to calculate the potential function and the electric field for the region between these two concentric right circular cylinders. So we need to calculate the potential in between these two cylinders in this region. Now, what do you think? What kind of a coordinate system we can use here? And what is the equation we can first consider? Can we consider the Laplace equation or the Poisson's equation? So here we are considering cylinders, therefore we can consider cylindrical coordinate system, and then we can use the Laplace equation. So we don't have any charges in between these two cylinders, therefore Laplace equation in cylindrical coordinate system, we have del squared V is equal to 0. So del squared V in cylindrical coordinate system, it is 1 over R double over double R double V over double R plus 1 over R squared double squared V over double psi squared plus double squared V over double z squared. So this is equal to 0. Now, when we consider this given situation, what do you think? So we have two concentric cylinders, and does the potential vary with z-axis? When we change the length of the cylinder, will the potential change? Or when we consider different angles, so if I consider potential here and if I consider another angle here, then when we change the angle, will the potential change? Will the potential change with Z? Will the potential change with psi? It's not going to change, right? Only the potential is going to be vary with this radius of the cylinder. So we can eliminate these two terms, this one and this one, because potential is not going to be vary with psi, or potential is not going to be vary with Z. Therefore, potential is only going to be very R. So when we consider psi relative to psi, V is going to be constant. Therefore, when we do the differentiation, this term is going to be 0. When we consider Z, with Z, V is going to be a constant. Therefore, partial differentiate this one, it's going to be 0. Then we only need to consider this part. So it's going to be reduced to one dimension. Therefore, we can write 1 over R d over dr R d V over dr is equal to 0. Then we can follow the general procedure to calculate the potential here. We just need to integrate this one to calculate the V. So try that one and let me know what is the equation that you can obtain for electric potential. Try that one. So we have d over dr r dv over dr is equal to 0. Then we can integrate both sides. So with integration, we are going to get r dv over dr is equal to a constant. Then we are going to divide both sides by r. Then again, we need to integrate this. Then we are going to get potential variation along r is equal to a ln r plus b. Then what can we do to calculate this value for a and b? How can we calculate value for a and b? We have two boundary conditions. When r is equal to 1 millimeter, potential is 0. Other boundary condition, when r is equal to 20 millimeters, potential is 150 volts. So we can apply those two boundary conditions to determine what is A and what is B. Try that one and let me know the answers for A and B. Apply boundary conditions and calculate A and B. So while you're solving that two values, if you had questions, you can ask. If you have any questions or if you need anything to be further discussed, please let me know. And also, if you calculate the values for A and B, type that answers in the chat or let me know the answers. So we are going to apply the boundary conditions here. When V is equal to 0 at R is equal to 1 millimeter. So V at R is equal to 1 millimeter, it's equal to A times ln 0.001 meters plus V. So the potential here is 0 is equal to A times ln 0.001 plus V. Then the second boundary condition, when potential at R is 20 millimeters, 0.02 meters is equal to A times ln 0.02 plus V. So here potential is equal to 150 A times ln 0.02 plus V. Now we have two equations and two unknown variables. By solving these two equations, we can determine what is A and what is B. So what are the values for A and B? Calculate those and let me know. At the meantime, if you have any questions or if you need anything to be further explained, please let me know. Calculate the answer here. So it should be, you will need a calculator to do this calculation. So here you should get something like 50.071. Then we can apply this value here to calculate B. So then we'll know what is the value for A and what is the value for B. Then we can substitute those values to determine the potential function. So the potential function is going to be V of R is equal to A. It is 50.071 ln R plus B. B value is going to be 345.9. So this is the potential function. So this is how the potential is going to be vary along the radius between the inside cylinder and the outside cylinder. Then how can we calculate the electric field? So to calculate the electric field, you can use E is equal to minus gradient of the electric potential. So here we are using cylindrical coordinate system. Therefore, del operator dabba V over dabba R and plus 1 over R dabba V over dabba psi direction plus dabba V over dabba Z direction. So the answer we got for that one, we considered potential is only varying along the radius, and then answer here, potential function, it is only dependent on R. Therefore, if we do the partial differentiation by psi and by Z, these two terms are going to be 0. Then we only need to have this term. So we have is equal to minus dabba over dabba R A ln R plus B in the direction of R. So here we will get minus A over R in the direction of R. And we know the value for R, value for A. So minus 50.071 over R in the direction of R. So this is the electric field in between these two cylinders. Okay. So is it clear how we solve this question? Any questions up to this point? ඔයගලන්ට අපහැදිලි තැන් එහෙම තියෙනවද අද මෙතන ඩිස්කස් කරපුවේ? Anyone? So I'm going to move into another example. In spherical coordinates, potential is 0. So R is 0.01 meters. So we have one sphere here. Along the surface of that sphere, the radius of that sphere is 0.01 meters, and on the surface of that sphere, potential is 0. And for another sphere here, where radius is 2 meters, potential on the surface of that sphere is 100 volts. Assume free space between the two concentric spherical shells. Find electric field and the electric displacement field. So in this question, it is already given. We need to use the spherical coordinate system. And in this one, we can see potential is only going to be vary with the values of R. So it's not going to be vary with theta or psi. Therefore, Laplace equation, so we don't have any charges in between these two spheres. So we can use the Laplace equation, and it is only going to be dependent on R. So V is not a function of theta and psi. So it's only going to be vary with R. Therefore, we have 1 over R squared over dabba R within brackets R squared dabba V over dabba R. It's going to be equal to 0. Then by direct integration, we can first say R squared dabba V over dabba R is equal to constant A. And then we need to do the integration again. Then we can obtain the potential function here. Potential function V is equal to minus A over R plus B. And then two boundary conditions are given. At R is equal to 0.1 meters, potential is 0, and R is equal to 2 meters, potential is 100. So we can apply those two boundary conditions and we can obtain the values for A and B. Then we know the value for the potential function. Once we know the potential function, we can easily calculate the electric field and the electric displacement field. E is equal to minus gradient of this electric potential, and electric displacement field is equal to epsilon naught times E. Okay, so that is how we can calculate the electric field and the electric displacement field once we know the electric potential. Okay, so now depending on the coordinate system, we can, depending on the given geometry, we can select most appropriate coordinate system, and if we can reduce our Laplace equation to a one variable by doing the direct integration, we can easily calculate the potential and apply the boundary conditions. Then you will know the unknown variables, unknown constants to the potential. Then using the potential, you can calculate the electric field and the electric displacement field using these two equations. Okay. So I think that's all I'm going to cover for today. Now, any questions from the content we discussed today, or anything that you need further explanations or any suggestions? Anyone? So if you have any questions, you can ask. Otherwise, let's meet on Monday again. Okay. So if you have any questions, you can ask. Otherwise, you can leave the session. Thank you very much.